in everyday life, then preparation procedures, what they do is they give me some fluctuations, and then I have some missing knowledge about which configuration is actually the case. So this would be states that are just probability distributions. In the discrete case, you would have probability vectors with entries that sum to 1. Continuous case, it would be, we get to that, continuous distributions or response functions. But there are many other possibilities. When we think of what comes out of a quantum channel, fluctuations, and then I have some missing, then what we sometimes knowledge about which configuration is actually the case. For example, so this would be states that are just probability distributed and not all the pure states. Also, there are systems that are subject to superselection rules, which forbid some superpositions, and many, many others. And you can ask the fundamental question, well, which ones can we actually get? Or which ones can we in principle get or plausibly obtain in nature? Right. And the idea now is that once we answer the second question, we can then apply this by devising a test of quantum theory via what's called theory agnostic tomography. And so theory agnostic tomography is the idea that we have a physical system in the laboratory, we test it in all possible ways, and we fit a probabilistic theory to it. Before going there, let me tell you how we can describe these experiments and what a probabilistic theory actually is. The starting point is that it's an operational theory. An operational theory describes a set of preparation procedures. Yeah? Think of all the procedures that are available in some regime of physics or in your laboratory or according to quantum theory. And then you say, well, some of these preparation procedures, they are essentially the same. Yeah, maybe when I press the button on one of the boxes, I get exactly the same statistics as if I pressed the button on the other box. They're just differently colored boxes. And I say that these preparation procedures would be equivalent if they give identical probabilities for all outcomes of all accessible measurements. Yeah, think of a qubit. If one preparation means 50-50 at random preparing the 0 or the 1 state, the other preparation procedure is a 50-50 preparation of plus or minus state, then essentially you prepare the maximally mixed state and your statistics is indistinguishable. So all measurements that you could do on that system would give the exact same probabilities. Yeah. A state in this picture would just be an equivalence class of preparation procedures. You group all the preparations together to give the same statistics. What I just described would tell you the maximally mixed state in quantum theory is just like a big box of all kinds of different preparation procedures, how you would get that state by doing something in physics. You can also look at measurement procedures. Measurement procedures are assumed to have a physical system as an input and to give you a classical outcome that you can read off. And then you say for any pair of measurement M and outcome K, I call two such pairs equivalent if the probability of this outcome given that measurement is just identical to that of the other outcome and measurement for all possible preparations. Yeah. If you group together these pairs, then what you find is an effect. An effect is then an equivalence class of outcome measurement pairs. And what you can do is you can pair these two together. You can say, suppose I prepare that state, I measure that effect. What is the outcome probability? Mathematically, you can do this by saying that the states omega live on some dual space A star, the effects live on some vector space A, and then you can combine them to get a number. So this is how you obtain general probabilistic theories. You have mathematically, you have a vector space, so your states live or your effects live. You have a set of normalized states and a set of effects. Okay. So in quantum theory, this is the easiest example. The vector space where everything lives is just the set of Hermitian matrices. The set of effects that give you a measurement outcome probabilities are just the POVM elements, so operators that have eigenvalues between 0 and 1 and are self-adjoint. The states are the density matrices, self-adjoint operators rho with trace rho equal to 1. And then you can combine two of these to get a probability with the trace rule. Mathematically, this means that you take the space and the dual space and you identify them with this trace in a product. That's how you compute probabilities in quantum theory. Classical probability theory So I should say that quantum theory over n outcomes will be denoted Qn in the following. And n can be finite or countably infinite. I can also think of a separable Hilbert space, for example. You can think of classical probability theory in a similar way. Now your vector space is just Rn, and your state space omega is the set of all probability vectors. So n probabilities, pi, they are non-negative and sum to 1. And the effects are vectors that all entries are between 0 and 1. And then you combine them with the dot product and you get a probability. Now your state space doesn't look like a ball in quantum theory, it more looks like a simplex. So you have a convex combination of finitely many deterministic states, basically. These are the classical pure states. Yeah. Here's an example of a theory that's neither classical nor quantum, and that's been studied sometimes in quantum information and foundations. It's called the generalized bit or gbit. This is a state space where, as you see on the right here, with a set of normalized states looks like a square. So you have one of the 4 corners are the 4 pure states, and the center is something like the maximally mixed states, and you have all possible mixtures giving you the square. When you now say, what if I have unnormalized states, then you can scale this thing, and then you get in the middle this cone of unnormalized states. Maybe forget some of the formalization here now. Yeah, that's a bit convex geometry jargon. But what you find is also that you get effects, which give you outcome probabilities, and they look something like a diamond. Comparing an effect with a state gives you probabilities. And it turns out that when you look at the system, that these 4 pure states, the 4 corners of the square, they turn out to be pairwise perfectly distinguishable. So the left upper corner can be perfectly distinguished from the right upper corner, but they are not jointly perfectly distinguishable. And this is a behavior that you cannot have in quantum theory or in classical theory. And this already shows you that this system is neither classical nor quantum. Good. Now, given that background, what is theory agnostic tomography? In a nutshell, the very idea is that you go to the lab, you isolate some physical system, and you perform as many preparations as measurements as possible. You fit a general probabilistic theory to the data, both a state space and a set of effects, and then you compare with the quantum predictions. And this has actually been done. So there are 2 papers on this, and I really admire those experiments. So I apologize to the authors for giving this really cartoon version of what they did. But the essential idea is what I write here. What they find, for example, is that they look at the polarization degree of freedom of a single photon, look at the data table, try to factor it into a state and an effect space, and then they find something like a bumpy qubit. So you get very close to the quantum predictions that the proton polarization is a qubit. But the authors here write also that there's, in principle, like it's a problem to these experiments, and that's a loophole that they call the tomographic completeness loophole. And this is the fact that you can never really be sure that you probed your system completely. So, you know, you think you have a photon with a polarization degree of freedom in your lab, and you try everything you can to scan over it and to do tomography in a sense. But perhaps there's some high energy physics that we see in 1,000 years from now in string theory or so, and there are actual other degrees of freedom of the polarization, maybe more dimensions to the Bloch ball that we don't see. We can certainly never exclude this, and this is an essential loophole that remains here. Now, given this, we can ask, well, is it really that essential? Can we perhaps also say something interesting if we're not assuming tomographic completeness, that we scan the system completely, and ask, what if we just see a low-dimensional shadow in some sense? Yeah. So let's drop the tomographic completeness assumption and say, we go to the lab, we have something like an effective physical system, which is just defined by the set of procedures that are available to us at the moment. Right? So you say, well, I only take into account what I can today in my lab, and I ignore what I might be able to do in the future, essentially. And if we now do this and we perform theory agnostic tomography on an effective physical system, and we obtain some, well, weird and perhaps noisy probabilistic theory as a result, then is quantum theory then a possible explanation, or is it a plausible explanation? Or would our data perhaps be able to falsify quantum theory as a fundamental description. So the question here is fundamental quantum theory a plausible explanation of a given effective general probabilistic theory? And this is certainly a topic that you have often in physics. That you think of an effective theory, maybe an effective field theory, and you hypothesize about a fundamental underlying theory, and you ask about the relation between the two, especially what the effective theory can perhaps tell you about the fundamental theory. So how do we then address this question in the case that we have probabilistic theories, an effective and a fundamental probabilistic theory? And the main idea will be to use the notion of contextuality in the version posed by Rob Spekkens, and to generalize it to arbitrary fundamental and effective theories. This will lead us to notions of simulations, of embeddings of theories. So let's get to that. Let me give you a quick recap of Spekkens' notion of contextuality. There are many other versions of it, contextuality, and I think they're all great and should be studied. For the specific purpose we have in mind, we think that Spekkens' version is the most useful one. So when you go back to understand what this notion means, just recall what I told you in operational theory. We have preparation and measurement procedures. And now what Spekkens introduces, also Harrigan later, is the idea of an ontological model of a system, such as a qubit. And this is nothing but a set of classical variables lambda that are somehow supposed to describe what is actually the case with your physical system. Right? So you would say, well, my physical system, the qubit, when I have a preparation procedure and I press a button, then what's actually happening is that some distribution over these lambdas, these hidden variables, is prepared. That's actually what's going on. When I observe an outcome K of some measurement M, what this means is that I've actually implemented some response function within classical statistics that picks one of the outcomes with some probability. And the probabilities that I see in my experiment are just given by the usual classical rule of computing probabilities. So you average over the preparation probabilities with your response function. Right? So just to illustrate what that formalism means, think of lambda now being a discrete variable, so that you don't have an integral but a sum. And suppose it's just dice, and you throw fair dice, and then you get a uniform probability distribution over the 6 lambdas. Your measurement could be that you ask, does it show a number that's larger than 3, yes or no? And then you would say, well, to the response function, the yes and the no response function, the yes response function will give you 1s if you have the outcomes 4, 5, or 6. No, if you have 1, 2, or 3. If you add them up, you get 1 everywhere. And you say that you get the probability of outcome K if you just average. So if you sum over all the lambdas of the probability times the response function. Yeah. Then you say, I want this to happen for my classical model, for the kind of hidden variable model of my system. It should reproduce the probabilities I see in the lab. Now, the crucial note, it turns out you can always do that. There's no magic to it. Quantum theory has many models of this kind. But here's something that you would also want to demand. You want your ontological model to be preparation non-contextual. And what this means is that you have 2 preparations, P and P prime, and suppose they turn out to be equivalent, so they give exactly the same statistics for all measurements, then you want to demand that this means that the distributions over hidden variables are just the same. Mu P and mu P prime are just identical. Why that? Well, the intuition is that why should these 2 preparation procedures give the same probabilities? Well, that's because all they do is essentially prepare the same distribution over the lambdas. That's very plausible to assume that this is the reason for why you have this equivalence in the first place. Similarly, you can introduce the notion of measurement non-contextuality and say, if some measurement outcome pair is indistinguishable statistically from some other one, then this is because the 2 response functions are identical. Right? And if you have both, then you would call the model non-contextual. Now, Rob argues at length why this is a natural assumption to make. I'll get back to that in a couple of slides. But certainly one thing that he shows that you can see is that if you have a quantum mechanical system such as a qubit, then ontological models must be contextual. They must be preparation contextual. So they cannot have these nice properties that we've just postulated. maybe ignore the last line. We can also say something about measurement contextuality, but I would refer you to Rob's paper for that. Right. So the rough intuition that Rob asks is like contextual models of some quantum system are implausible because they involve some amount of fine-tuning. You would say in the laboratory operationally, P and P prime can never be distinguished statistically. They are really identical. But the model assumes that ontologically, and what's really going on is distributions over lambdas that are different. And this is seen as implausible for many reasons. This has a couple of advantages. I think it has this conceptual clarity to this principle. It formalizes essentially an instance of Leibniz's principle of the identity of indiscernibles, that things you cannot actually distinguish operationally should be identical ontologically. It applies to a wide range of physical phenomena. You don't need to restrict yourself to projective measurements or dimensions of systems larger than 3. You can do directly experimental tests with it. We are non-contextuality inequalities, for example. Now, what we do in our work is now we take this notion and we generalize it to the case that the fundamental theory that you think underlies essentially everything of your data, the fundamental theory is not necessarily classical like these hidden variables, but for example, quantum or otherwise. And when we do this, we arguably obtain all the advantages of Spekkens contextuality in a more general framework. Good. To do so, we talk about simulations of one theory by another and embeddings of one theory into another. So think of, for example, an effective probabilistic theory that you have found in the laboratory by doing, for example, tomography, theory agnostic tomography. Maybe you find something like this weird gray state space. Then you think that, well, somehow this must have been simulated or simulated by the fundamental probabilistic theory that's really governing the laboratory physics fundamentally, microscopically. For example, I could believe that fundamentally quantum theory is governing laboratory, or it's fundamentally classically perhaps. Maybe I want to test that assumption, whether that makes sense. Spekkens contextuality considers the situation where A, your effective theory is quantum theory, and you want to ask whether fundamentally the fundamental theory is classical probability theory, whether that makes sense, whether that is plausible, that your fundamental underlying physics B could be classical. We are, however, mostly interested in the case where A is just the effective theory you find in your laboratory, and B is quantum theory. And you ask, fundamentally, quantum physics should describe laboratory physics. Now, what this means is that when you have a preparation procedure and you're effectively preparing some state omega A, that means that actually fundamentally preparing some other state omega B that you cannot directly access. Now, however, you realize that there are many ways in which you want to prepare omega A, like in quantum theory, 50-50 mixtures of up and down or left and right. But this could correspond to different states in the fundamental theory, omega B. Depending on how you do that, it might just mean that your underlying states actually differ, as would be the case in Spekkens contextuality. So what you do is to say, for any such effective state omega A, that's a fixed state, I collect all these possible fundamental realizations that happen to be prepared when I try to prepare omega A. There's a set of many states, omega B of omega A. That's how I denote it here. A set of possible fundamental states. An example is given by what's called the Hollywood projection, where you say, where you simulate the generalized bit, the square bit that I've talked about earlier, with a classical 4-level system. So essentially you say, well, in the lab, I see the square at the bottom, but fundamentally I have a 4-level classical system. All I see is this kind of shadow, this projection. So what you would have that, you would say that the corner states of the square, the alpha plus, alpha plus plus, alpha plus minus, and so on, they are actually simulated by 4 perfectly distinguishable classical states, the beta plus plus, beta minus minus, and so on. But just probability distributions 1, 0, 0, 0, 0, 1, 0, 0, and so on. But when you now ask, if I do that, how would the mixed state in the center of the square be simulated? Then you realize that it would have to be simulated by more than one classical state, it would have to be simulated by all the classical states beta prime that are on the blue line. So why is that? Well, think of preparing alpha prime in the center of the square by preparing two of the diagonal states, maybe alpha plus plus and alpha minus minus, 50-50 mixture. If you do this procedure, then on the classical level, you get a 50-50 mixture of beta plus plus and beta minus minus. So you end up on top of that tetrahedron. But if on the square you prepare it differently, say it's a 50-50 mixture of alpha minus plus and plus minus on the other diagonals, then on the classical level, you end up with a very different description where you end up at the bottom of the tetrahedron, somewhere else on this blue line, right? So this is a notion of preparation contextuality. The fundamental states that are actually prepared do not only depend on the effective state alpha prime that you think you have prepared, but it must also depend on your procedure, like how you have prepared that state. And we think that this is an instance of an implausible fine-tuning, because the statistical difference between all these beta primes here, among all these fundamental states, they're somehow miraculously washed out so that you don't see them in the laboratory on the effective level. It's a bit like models for Bell non-locality that postulate superluminal information propagation. Somehow you have to have a mechanism that hides the superluminal propagation so that you cannot in your lab build a Bell telephone, which is an instance of fine-tuning. Right. So then what we define is we say what is a simulation up to error epsilon of an effective probabilistic theory A by a fundamental theory B. Well, to every effective state omega A, you have a set of simulating states on B that I denote omega B of omega A. Very effective effect on your lab, you have a set of simulating fundamental effects EB. Right? And when you pair them together, then you get the same probabilities up to error epsilon. Okay, that's the first condition. The other is they say, well, what would the simulation do? Well, if I so one other thing that we need is that mixtures of simulating states are valid simulations of mixtures of states. So what do I mean by that? So suppose you have a procedure where you prepare with probability lambda, you prepare effectively state omega A, and with probability 1 minus lambda, you prepare effectively state phi A. Then what this does fundamentally, it prepares a simulation of omega A with probability lambda and a simulation of the other state with probability 1 minus lambda. And so the mixture of the simulations is a valid simulation of the mixtures. Yeah. So that's something that you obtain here. And also, how do you simulate the impossible effect, that the impossible measurement outcome that has probability 0 in all states? Well, with the impossible fundamental state. So that's also something you always can have. Yeah. And you would say that the simulation is non-contextual if every state is simulated by exactly one fundamental state, and every effective element is, every effective effect is simulated by one fundamental effect. So it's one-to-one, right? In the special case that your fundamental theory is classical, we can say two things. First, we can prove a theorem. It tells you that every GPT, every theory A can be simulated classically up to arbitrarily small error if you make the dimension large enough. The simulation can be measurement non-contextual, but it must be in general preparation contextual. And that's essentially what happens in the Hollywood projection in this picture. This is preparation contextual, like one effective state must be simulated by many other fundamental states. And that's something you can do in general for all probabilistic theories with a dimension bound. So in a way, that's very boring. Yeah, contextual simulations are always possible in all cases, essentially. And so what Spekkens calls an ontological model of an operational theory, this is nothing than an exact simulation in our terminology, by classical probability theory. So this is just the same thing that Spekkens defines in the special case that the fundamental theory is CN, is classical. And the simulation is preparation non-contextual or measurement non-contextual exactly if and only if Spekkens' ontological model has this property, right? So in this sense, if B is classical, everything reduces to Spekkens' notion. But we do it more generally because B can now everything, in particular B, the fundamental theory can itself be quantum. Turns out that non-contextual simulations have a very simple property. They are embeddings, linear embeddings. So this means that in the effective theory, when you prepare a mixture of states in the effective theory, this must be simulated by a mixture of fundamental states. And you have a linear map that maps the effective states, a linear map psi that maps the effective states to the corresponding fundamental states. So maybe forget this, a bit too mathematical, but you have two GPTs, A and B, and then you say, what's an embedding? Well, it's kind of linear maps. One linear map psi maps the states of A to the states of B. Another map phi maps the effects of A to the effects of B, and then you want the probabilities to be preserved up to epsilon error. And then you can show that every epsilon simulation, every non-contextual epsilon simulation is exactly an epsilon embedding and vice versa. Okay. So if you want to ask what's non-contextually simulable by classical quantum theory, you have to ask for what are the possible embeddings into classical quantum theory. Okay, so to test Spekkens non-contextually experimentally, people have come up with the notion of inequalities, of non-contextuality inequalities. For example, if you have these 6 preparations and measurements on the qubit, you can write down a certain inequality. Please see the paper for details. We say this quantity that you can measure in the experiments must be upper bounded by 5/6, classically for any classical ontological model, but quantum theory gives you a value of 1, right? In the qubit, for example. It turns out that these non-contextuality inequalities are very closely related to our notion of epsilon embedding. Here, for example, it tells you that if epsilon is less than 1/6, if your error is less than 1/6, then the qubit and its real version, the rebit, cannot be epsilon embedded into any classical system. That's kind of our reformulation of contextuality inequality. Right? This tells you also that if you have a proof of epsilon non-embeddability of your data, this allows you to experimentally falsify non-contextuality. Good. Now, what can we say about embeddings into quantum theory? In the end, we want to test quantum theory experimentally. So we get some data, some experimental GPT, and then we want to ask, does it have an embedding into quantum theory, yes or no? That's an interesting question to ask. What can we say about this? So which general probabilistic theory actually admit of a non-contextual simulation by quantum theory? So it can be embedded into some QN, some n-level quantum system, for example, exactly. And one example is classical probability theory. That's perhaps the simplest example. You can take a probability vector and map it linearly to the diagonal matrices. And then you do the same with the effects. And when you prepare them, you get exactly the same probabilities. Geometrically, you can think of a classical bit as like this line, and you embed it into the north and south pole that's part of the qubit, right? Also, quantum theory over the real numbers can be trivially embedded into a standard complex quantum theory. Real qubits are a circle, like the equatorial circle. You can embed it into the Bloch ball, essentially. Yeah. Now let's see what we can say in general if we focus on so-called unrestricted GPTs. So these are mathematically very nice GPTs where you say the states and effects are perfect duals of each other. So every vector that you can write down, which would give you valid probabilities on all the states, is actually an effect that you can implement. What about those? Those are not the ones. So quantum theory has that property, also classical probability theory. It's not what you would find in the lab. You would find some noisy stuff where not all effects can be implemented. But let's assume for now that you have an ideal unrestricted GPT of that kind. Then we prove in our paper the following theorem: an unrestricted GPT can be exactly embedded into finite quantum dimensional quantum theory if and only if it corresponds to what's known as a special Euclidean Jordan algebra. So in less jargon of mathematical physics, these are essentially those state spaces. Quantum theory over the real numbers, we've talked about that, can be embedded right into standard complex quantum theory. Certainly complex quantum theory as well with the identity map, but also quaternionic quantum theory can. You can have Bloch ball state spaces of arbitrary dimension d, and you can have something like block matrices of those, so direct sums of those. And this includes classical probability theory and also quantum theory with superselection rules, where states are discriminated by block matrices. And that's everything. These are the only ones that you can embed. in a non-contextual way in quantum theory, and which are unrestricted in the way that I described. So this tells you, for example, we should not, and in fact are not surprised if we find such state spaces in the laboratory. There are plenty of classical state spaces that we encounter every day, for example. So this focus on unrestricted GPTs, however, gives us a nice mathematical physics result, but it's irrelevant for the experiments we have in mind. Experiments will typically yield restricted or noisy GPTs. Your setup is something like effective channel that shrinks your state space. You cannot have all pure states and all pure effects, but something smaller. Right? So then if you have a goal to experimental testing quantum theory, then we need to do more generally say something about restricted theories. So we perform theory agnostic tomography on an effective physics system in the lab. And what we want to do is we want to certify that the theory that we find is not epsilon embeddable into quantum theory, and epsilon describes the experimental uncertainty. And if it succeeds, then this would challenge quantum theory. So you think of, well, maybe the system in my lab, photon polarization, for example, is described by this black state space like a ball or so, omega A. I cannot implement all states, but only finitely many of them. So effectively I implement, for example, this blue state space here, this polytope. But since my data is finite, the statistic is finite, I will get some distorted version of that, kind of sticking out of it. This is like this brown one. Then I want to test if this is embeddable into quantum theory up to error epsilon, yes or no. How would I certify that it's not embeddable? And this is the question that I want to turn now in the last part of the talk. How do we certify non-embeddability? Right. What about restricted or noisy GPTs that we find in the lab? Can we certify that there is not even an approximate non-contextual simulation by quantum theory? And I will show you that we can in some special cases, and we have a general scheme. As a special case, which kind of gives you a proof of principle, let's look at the square bit again, the gbit. Yeah. It's still an unrestricted theory, but whatever, as a proof of principle, let's look at this. Yeah. So what we prove in our paper is, in fact, the gbit cannot be embedded into quantum theory of any dimension or even infinite dimensions up to an error that's better than 10%, like this 0.1014 or so, which is not the optimal bound, but something we can prove. So if your error is less than that, then the gbit cannot be non-contextually simulated by quantum theory. If you find a gbit in your laboratory with statistics that's better than this epsilon, you should be really surprised. Yeah, that's interpretation. This would kind of challenge quantum theory if you find that in your laboratory. What's the proof sketch? Well, I don't want to go into details, but basically it works with the observation that the four corner states are pairwise perfectly distinguishable under some noise, then almost perfectly distinguishable. And if you have four quantum states that are pairwise almost perfectly distinguishable, they must span a three-dimensional subspace of your matrices. And so you get a contradiction, essentially, with a gentle measurement lemma or whatnot. Okay, so we can do this in these special cases. There's also a general method that we propose that works in principle for a large class of probabilistic theories, even restricted ones, which use a notion of known facts about Bell non-locality on two virtual systems. So essentially what we show, the details are in the paper, that if you have a theory A, and that can be embedded into quantum theory up to epsilon, either in some finite dimension n or in infinite dimensions, if it can be embedded approximately, then all the Bell correlations for all non-signaling correlations of AA, of two copies of A, must be order epsilon close to quantum correlations. Well, okay. So what does this tell you? Well, here's an example, again, for a mathematical physicist, something nice that this tells you. For example, if you have now two quaternionic quantum systems, two quaternionic bits, for example, and you look at what are all the possible non-signaling correlations on AA on two copies, then this tells you, since quaternionic quantum theory can be perfectly embedded into complex quantum theory, tells you that they must all be simulable within standard complex quantum theory. So for pairs of systems, quaternionic quantum theory cannot give you new correlations. It's kind of well known in folklore in the field, and you can read papers by Howard Barnum, Matthias Kleinman, and so on. But this is just an example consequence of this lemma. Another consequence is if A is an even-sided polygon, like the square, for example, or the picture that we have here, then some states on 2 copies of that violate the Zittelson bound of 2 square root of 2 for the Bell-CH-SH inequality. And so if you think of the gbit again, the square, and you take virtually mathematically imagine now 2 gbits, then the state space allows for Popescu-Rohrlich correlations that exceed the quantum bound. And this tells you that a single gbit cannot be embedded into a single quantum system. That's what this lemma also tells you. Right? So in general, for these even-sided polygons, we can now infer from these known results that we can compute some epsilon such that the state space cannot be epsilon embedded. So an error close to 0 is impossible for an embedding into quantum systems of any dimension. So I should say that this is just a proof of principle and an interesting relation to non-locality. It's not the best method or an optimal method. And it's somehow still an open question. How, when you find a GPT in your laboratory, how would compute the optimal epsilon? So you say, I cannot embed that system by better than this error in quantum theory. What's the best possible epsilon? We still don't know. Might be some work by Armin Tavakoli and colleagues that might help us doing so. But this is, let's say, a proof of principle that we could do it, and then we could apply it in principle in experiments. Okay, so with that, let me summarize. So what we've done in our paper is we have generalized Spekkens' notion of generalized non-contextuality to a kind of methodological principle. And that principle says that processes, say preparations, measurements, that are statistically indistinguishable in an effective theory, they should not require explanation by multiple distinguishable procedures in a more fundamental theory. Spekkens would say that a given quantum state, if I have different procedures that prepare the same quantum state, this should not require different distributions of the hidden variables. And we say this should be true for arbitrary effective theories and arbitrary fundamental theories when we think that the effective theory arises from the fundamental theory in a plausible and natural way. And we've analyzed that by studying approximate simulations and embeddings of one GPT into another. I should say people have criticized us, and I think rightly so, for overstretching the notion of contextuality. So we're kind of editing our paper now. We might use a different word in a future version, but for now we call this, it's a generalization of generalized non-contextuality. We've classified all unrestricted GPTs that can be exactly embedded into quantum theory and given some methods for the certification of the impossibility of an approximate embedding into quantum theory. It's not optimal. The goal is still that we can find better methods for doing so. And as we've shown, this admits a novel experimental test of quantum theory, similar to, very similar to the theory agnostic tomography that people have done before, that does not suffer from this tomographic completeness loophole, at least not in the same way that people have described in this earlier work. Right, so you find paper on the archive here. And with that, I would like to stop. And thank you very much for your attention.
Thank you, Markus, for this very thought-provoking talk. I'm sure people will take some more time to absorb it fully. And I urge people to actually have a look at this archive paper and to understand it deeply. Now the session is open to questions.
Tavis, I have a small question.
Sure.
Yeah, Markus, how are you? I'm Panigrahi, if you remember.
Yes, hi, good to see you.
Yes,
how are you?
Yeah, I just wanted to know, has somebody done some experiment on IBM platform? Or
say it again, or what?
This IBM quantum platforms. Has somebody tried this kind of thing, experiment?
That's such an excellent idea. I like this. I don't think somebody has done that. No.
Yeah, I'll try to put some student into it. Let's see.
Nice. Yeah, that's very nice. Because sometimes people complain that it doesn't reproduce the statistics that you would expect in very weird ways. But yeah, that would be really nice.
Okay.
I had a question. You said about approximate simulations and embedding. Are these kind of problems can be formed in terms of SDP? Is it possible?
So I would expect that embeddings into quantum theory or non-embeddability can be checked with some kind of hierarchy of SDPs.
Okay, so the constants are the constants linear here? What will be the constants?
So it's a good question. It's something we want to look at. We haven't really fully looked at, but you can, for example, look at existing work by Armin Tawakoli and co-authors, where they don't look at full state spaces, but at contextuality inequalities. And then you ask, for a given contextuality inequality, what is the classical bound? This is very easy to answer, but you can also ask, what's the quantum bound, the analog of the Zillerton bound? And then they give a convergent hierarchy of SDPs, as far as I understand, that allow you to numerically determine in a very powerful way the quantum bound. If you want to apply this to a full GPT that you fit to your data, then this would be an analog of somehow infinitely many inequalities that correspond somehow to the convex structure of that thing, like which preparations are operationally equivalent to which other preparations. And I don't know whether it could be adapted to that case, but it would be very nice to look at this. But I expect it can be adapted somehow to this problem.
Okay, thank you.
Thanks.
Yeah, there is a question. Like, I couldn't get that point, like when a preparation strategy is non-contextual in nature, but it's like the statement was like it's implausible to accept that nu p is not equal to nu p dash when p and p dash are equivalent in nature. So why is that implausible to to get?
Yes. So for the plausibility, so first thing to say is, if you look at the plausibility of this notion of non-contextuality, I would refer you to some existing literature by Rob Spekkens and co-authors. They are very elaborate and detailed in their conceptual discussion of why this is non-contextuality is a natural assumption. They refer typically to what's called Leibniz's principle of the identity of the indiscernibles. We say, here are two procedures, neither now nor in the future, nor with whatever exists in the universe, I will never be able to distinguish those. Then you should expect that this means that these procedures do the same thing fundamentally. So ontologically, this physics is just the same for both. That's, I think, the principle underlying this, and that you can discuss in less or more detail. For more detail, that's like Spekkens' version. I would just think of it as some kind of fine-tuning principle. It can certainly be violated. So you certainly, for example, here's an example. You could say, you could program an iPhone app on your mobile phone that simulates a Popescu-Rohrlich box or a singlet state between you and your friend who's far away. But that would have to involve signaling. You would have to send data back and forth to do the simulation. This would be manufactured in a way. So you can always manufacture contextual simulations. But for systems that you actually discover in your laboratory, that you test, you would not expect this kind of fine-tuning to appear. And then that's my intuition here. A lot more would have to be said about this. There's a nice recent paper by David Schmidt and either him alone or some co-authors that's called Debunking Some Objections to Generalized Non-Contextuality, where I think he goes in quite some detail of objections to this assumption that you might have and why this is a plausible assumption, for example, but there are more papers than that. We're kind of just like standing on the shoulders of those people, if you want, right? And say, we just have similarly good reasons to assume this notion of non-contextuality than Spekkens and co-authors have. So if you doubt one, you should doubt the other. But if you think one of them is plausible, you should find probably the other one plausible as well.
Thank you. Thank you for the references.
Thank you.
I have a question.
Yeah, go ahead, please.
Is the fundamental theory and in effective theory, the state space in fundamental theory should be smaller than the effective theory state space? Is it?
So maybe you can tell me in a minute why you would expect this. So I would rather expect that the state space of the fundamental theory is larger. So intuition, like when you think of statistical mechanics, when thermodynamics really has just a handful of parameters, temperature, pressure, and so on, the configuration of the actual gas molecules spans a much larger state space. And in fact, when you think of something like the Hollywood projection, for example, maybe let me not go back, but this picture here on the right top, the fundamental theory is the tetrahedron, and the effective theory would be the square, and the square is lower dimensional. So you'd say that some sort of coarse graining, or in other words, some degrees of freedom become invisible effectively. You cannot resolve them somehow. So this is why I would think it's the other way around, and you would have arbitrary, like a higher dimensional fundamental theory. Does that make sense? Or maybe you have another intuition?
Yeah. So the same state in effective theory can be obtained in different superposition of the fundamental theory states, is it?
Yes, the different ways.
Different ways.
In different ways from the fundamental theory, yes. Since you want to reproduce all probabilities, you need at least as much freedom in your fundamental theory as you have in your effective theory. So the fundamental theory should have dimension at least that of the effective one. That's kind of easy to see.
Okay, thanks.
That would be much larger in principle. So we're here really ruling out even infinite dimensional quantum models of, say, this two-dimensional gbit. So.
Okay, thanks. Oh, sorry, the gbit is like the effective theory state space.
In this picture, yes. I should probably have drawn it the other way around to have the same picture that I use with my hands. So sorry about that. When I mentally depict the effective theory is somehow up here and the fundamental one down there. This is like upside down, the picture with the Hollywood projection. Yes. Maybe because it's in Hollywood's book like that. Yes. Hope that's not too confusing.
Thanks.
Anyone else who has a question? Okay, if not, then Markus, thank you very much for this very interesting talk.
Thanks very much.
I'm here.
Hi.
Hello.
Yeah. So our next speaker for this session is Bob Coecke. He is the chief scientist at this Quantinuum. This is a quantum computing company. Before this, he had been on a distinguished chair at Perimeter Institute. And Bob does actually very different and very interesting kind of work. He is famous for introducing a sub-area of quantum mechanics, which goes by the name of categorical quantum mechanics, which involves interface with, pictorial view of things, music, and he even connects to things like computational linguistics. So, and for students, you might find online it's very interesting lecture notes called Kindergarten Quantum Mechanics. I urge people to have a look at it. So completely pictorial view of whole of quantum mechanics. So I'm sure today we will get a glimpse of this very interesting view from Bob. The title of his talk is From Quantum in Pictures to Practical Natural Language Processing, Music and Understandable AI.
Okay,
Bob,
thank
over
you.
to you.
So I'll start with, I'm going to close my door. People are too loud here. Oh, okay, here we are. So I'm going to share my slides.
Yeah, sure.
Share screen. So where are those are the slides I want to share. Share. And view enter full screen. Okay, here we are. So yes, my name is Bob. I'm the chief scientist at quantum computing company Quantinuum, who are actually going to make a very big announcement today, later in the afternoon in this time. I'm an emeritus fellow at Wilson College. They effectively organized a retirement party for me, so that was very interesting. And I'm distinguished visiting research chair at Perimeter Institute. So that's my second affiliation. Okay, so just to say a bit more about my history. For a long time, I was a professor at Oxford University in computer science. I'm a physicist, but in the sort of stuff I was doing, I wouldn't have had a chance at the time to get any appointment in the physics department. So the Perimeter Institute is a very nice thing to get this now. So we had a very big group. This was Samson Abramsky and myself. This was a big interdisciplinary group with many people many of which actually moved with me to Quantinuum. In 2020, I left Oxford University. Well, I'm still there. I'm still teaching and still supervising, but in terms of like a faculty place. And then I joined something which was called Cambridge Quantum. First Cambridge Quantum Computing and then Cambridge Quantum. And I became chief scientist there. But then again, in 2021, Cambridge Quantum was no more. And the reason, I mean, it's not that it vanished. Basically what happened is it merged with part of the big American company Honeywell. So part of Honeywell split off from Honeywell, the part which were building quantum computers, and they merged with us. And this afternoon, there will be a big announcement again concerning building quantum computers and bringing them to a next level. So that's where I'm now. Besides my global role in the company, I also have my own team in Oxford, and we focus very much on sort of the interface between artificial intelligence and quantum. And so a lot of these people here actually moved with me. Some of those names will come up in my talk. Okay, so that's our logo. So what this stands for a C and an I, compositional intelligence, because I mean, I see no reason why intelligence has to be artificial in the first place. Like, we are intelligent and we are not artificial to start with. And then compositional is basically the sort of structures we try to bring in. There's now a lot of debate and chat, especially after Hinton announcement that the brute force machine learning stuff may be quite dangerous for broad use. So the meanings in that direction are clearly growing. And so you need something that's more interpretable. And what we are doing is an example of more interpretable in AI. It's kind of nice that it also looks like a Q. So it's quantum compositional intelligence, if you want to. This logo was designed by one of our team, Konstantinos Mechanisidis. And I'm going to now take a time machine back in time to close to the beginning of the previous century, and where the language that we use to talk about quantum came about. So this is John von Neumann. John von Neumann is the father of the Hilbert space quantum formalism, which pretty much everybody still uses today. And he published that formalism in a book in 1932. In 1932, he published this. But in 1935, something very interesting happened, which you don't see much. So John von Neumann basically denounced his own Hilbert space formalism only 3 years after publishing his book. So I would like to make a confession which may seem immoral. I do not believe absolutely in Hilbert space no more. And then a big portion of von Neumann's career, as far as physics is concerned, was to try to look for alternatives for Hilbert space. One thing was called quantum logic. He also came up with phenomenal algebras and things like that. It's fair to say that none of them actually are now at anywhere close to a status that it's a substitute for Hilbert space. Honestly, they all vanished. They basically all vanished, and they're only in very marginal ways still being used. So on the other end, I should say that each attempt of von Neumann to come up with a new quantum formalism resulted in an entirely new field of mathematics. So he wasn't a complete failure at all in that extent. Now one thing I should say here is the idea von Neumann had, because he's also one of the fathers of quantum foundations, is you need to focus on what's the most important feature of quantum mechanics, what is the characterizing feature, and then we should conceptualize this and maybe abstract it and formalize, and that's the path towards a new quantum formalism. And for von Neumann, the most important thing about quantum mechanics was quantum measurement. What happens in the measurement process? For example, quantum logic was like, if you want to reason logically about quantum system, but the fact that you have collapse sort of complete changes your logic completely and logical structure. So these were the things von Neumann was focusing on. And most other people who were considering the foundations of quantum mechanics always had this particular focus on measurement, which was always at the core of quantum foundations. Now, this is Schrödinger. So Schrödinger was around at the same time. And Schrödinger had a very different opinion than von Neumann. So he's talking about here, this is his paper, also 1935, same paper, same time as when von Neumann denounced Hilbert space. And he's talking about two systems, when two systems, blah, 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 and then he starts to talk about how quantum systems behave when they come together. And then he says, I would not call that one, but rather the characteristic trait of quantum mechanics, the one that enforces its entire departure from classical lines of thought. So Schrödinger's view was the most important thing about quantum mechanics is the tensor product, not the measurement process, is what happens if you bring two systems together. And like I said, pretty much everybody in the foundations and quantum formalism was following von Neumann until fairly recently. And that's with a paper with Samson, Abramsky, and me wrote, which was the start of categorical quantum mechanics, which was mentioned earlier. And so basically, we kind of start to realize Schrödinger's view by coming up with a formalism which takes composition of systems as a first-class citizen. So it was actually, in order to make that meaningful, we also move away from a perspective of states, describing things by states, which are sort of static entities, to processes. So we have a theory of processes, and these processes can be composed sequentially, but also in parallel. That's actually the base, that's a monoidal category. There's nothing more to it. You've got processes which can be composed sequentially and in parallel. So we used this framework of monoidal category theory, and then we added some structure to it, a tiny bit of structure, a little bit of structure, and then we were able to basically define unitarity. We could derive things like quantum teleportation. And so we had already a quite expressive formalism with very little ingredients. There was like Born rules, there was number. So it started to look like a quantum formalism. This is now a paper which is quite famous. But the problem with this is not everybody is like a hands-on in category theory. You don't even have to be hands-on in category now, but at the time this was very much formulated as a category theory paper, and it's not everybody's bread and butter. But okay, so let's go to somebody else. So this is Roger Penrose, also at Oxford, also Nobel Prize winner, of course, for black holes and stuff. But something else Roger Penrose did was at some point, and he started this already during his undergraduate years, when he was learning general relativity. He really didn't like this sort of indices, which people use in tensors, like the Einstein notation type stuff. He hated it. And he kind of realized that you could equivalently represent these things by graphical entities. So you see here this QIABCFG, he replaces by a blob or a box or whatever you call it, with some wires coming in and some wires coming out corresponding to the indexes, which it has. And he came up with notations you see for many other tensors. So this goes back to the 60s, I think, to the 60s even, definitely early 70s. And it only appeared in one paper, really. It only appeared in one paper, in an appendix even, I think, of Penrose. So it was never a prominent thing in the literature. It was just a tool which you use like behind the scenes. Now, these two people are two category theoreticians, André Joal and Ross Street, and they actually realized that monoidal categories I was talking about earlier and these sort of diagrams Penrose was drawing are exactly the same thing. Or they're equivalent for all practical purposes. I can't go in what the precise notion of equivalence is because it's quite complicated, but you never have to, you can just think that they are the same for all practical purposes. That's kind of what it means. And so I wrote a paper which was earlier mentioned, Kindergarten Quantum Mechanics in 2005, which was pretty much the same content as the previous paper with Samson, but which was not formulated in terms of category theory, but rather in these sort of Penrose-like pictures. It was the same content, but now Penrose-like pictures, so much more easily accessible to a broader audience. And at that point, I mean, the plan for me was, can we, on the one hand, complete this theory of categorical quantum mechanics, so turn this into a full-blown quantum formalism in which you can do everything, which you can do in Hilbert space, or equivalently, can you come up with a purely diagrammatic presentation of quantum theory? So can we also have all these ingredients that we would need to axiomatized in category theory? Can you also always turn this in a diagrammatic way? And then the third way to say it is, can we formulate quantum mechanics as a theory of processes, where processes and their composition are the main actors? And so this is the sort of language one uses in there. So this is the main axiom you find in kindergarten quantum mechanics, and all it says is, if you got a bent wire, then you can yank it. It looks like a really silly axiom, but it's actually this is the sort of thing that lets you derive teleportation. This actually, in a logical sense, is sort of like a deduction theorem, although it looks very silly. And then if you got a box like that here, so you got this box, and so we typically in this talk, in this part of the talk, we will read these diagrams from bottom to top. So what you got here is basically a box, which you think of like an input-output device. And the wire bends the output into an input and the input into an output. As it turns out, this corresponds exactly to taking a transpose in linear algebra. So this is the way you can define the transpose during this cup and these cap-shaped wires, which you also see in this equation. And then you can then do just the following. You can just yank the wire, and then that box rotates 180 degrees. So actually, you have now derived that just rotating a box with 180 degrees is pretty much the same as taking a transpose. And so you can have an entire presentation of linear algebra with transposes, conjugates, unitarity, inner product, and all the sort of stuff from linear algebra just represented within this language. So that's something you find in this kindergarten quantum mechanics already. Now, okay, so these were the early years, 2005. We weren't able at all to derive or describe anything you can do in Hilbert space quantum mechanics. We are nowhere near at that time. But then 13 years later, there is this book, which I wrote with Alex Kissinger. And this effectively is a full course quantum computing, which is still being taught at Oxford by Alex Kissinger, and which I had been teaching for a long time. But this is a full-blown course quantum computing, and everything is presented in terms of this picture that I was talking about. So the theory, of course, advanced quite a bit to actually achieve that. And what we do, it's quite a big book, because, of course, we're not going to teach people only diagrams, because then they can't read anything else. So in this book, we start introducing everything by means of the diagrams, but then we derive linear algebra from the diagrams. We derive linear algebra, we derive the usual Hilbert space formalism, all from the diagrams. And then again, these pictures are quite big, so you easily get a big book, but we typically teach this in 20 hours. So the number of lectures to teach this is typically 20 hours. So it's much less than it may appear at first. Okay, now it is a university level book still. I think when we wrote this, what we had in mind is like university students, mainly who have some linear algebra background already, although we derive it, but it's probably much better if you have it already to actually get through all that stuff and so on. So it's definitely not kindergarten quantum mechanics. It's definitely not for kindergarten. Okay, now we are 5 years later, and now there is this book. It's new. It's called Quantum in Pictures. It's out since 1 or 2 months. Unfortunately, at the moment in India, it's only available as Kindle. We're working on it to change that. There's a reason we did it. We actually published this as our company, just to have full control. And I can say the philosophy behind this publication. But since we are not an established company, it's not so easy to actually do all of that. So we use something which is Amazon print on demand, which gets printed in the country you buy it. So you don't need distribution, you don't need storage, nothing of that. But it's not available in all countries, unfortunately. But now we're working on it. We're trying to get a distributor who can actually bring it to everywhere. But so for now, it's available as a Kindle in India. And this is really a book that is readable by people who don't have any maths background and want to learn about quantum. So we already have reviews from, like, I'll show later, from a 10-year-old, for example. So this is really a quantum formalism accessible for people without mathematics, but it's but it essentially covers the same content as we cover in the big book. So it's pretty much a full-blown quantum computing course without the Hilbert space formalism. So there's things in there which you don't even find in regular courses, like measurement-based quantum computing, no broadcasting theorem. So there's some pretty advanced stuff in there, but presented in a way that everybody who wants to can pretty much learn this. Now, what is soon going to be forthcoming and available everywhere in the world without any restriction is a lecture series of that book. And we're going to just put this on YouTube as a lecture series, so everybody can watch the lectures of this entire book. And that'll be soon put online on YouTube. Okay, I'm going to briefly take to like a tiny bit of the content in this book, just to give you an idea on how this formalism has evolved. So we already talked about wires and boxes. So basically the idea is you think of a wire as a system and of a box as a process that acts on that system. So this could be like a wire could be a quantum particle, the box could be like a quantum gate or something like that, or it could be a measurement from quantum to classical, or it could be just an electricity device or a water pump if your wires are places where water flows. So it's just a generalized thing. And then what you can do is you can compose them. And you see, we both compose them sequentially. Some boxes come before other boxes, and also in parallel, some boxes are besides other boxes. And that's sort of the basic formalism. And you have these two composition operations sequentially, and then the composition of systems, well, here and processes. If you see two wires side by side, it just means these are two systems. So we actually start effectively, but we've given composition of systems the sort of lead role in this game. It is the lead player. We saw this equation already, and so let me now go in more detail. Now that I told you that these wires correspond to systems, then you see the cup-shaped wire at the bottom is basically something which has no inputs. If you treat this as a box, and two outputs. So it's a state of two systems, and actually this is supposed to be the Bell state. So this cup-shaped wire is actually the Bell state. Whenever you got a box without inputs, it will always represent a state. On top, you got like a cap-shaped wire, which you want to treat as a box too. And this is like an effect or a test. This is actually the Bell effect. And the Bell effect corresponding to the Bell state just by going from a cat to a bra. So that's really what the thing on top is. And so if you think about this now, this is actually a non-trivial equation. You got an open wire left bottom, so this means there's a system particle coming in. Then you got this cup-shaped wire. This means a Bell state is created. So suddenly we got three particles going on, and then on the top you've got this Bell effect, which means two of the particles vanish in a post-selected measurement, and then this equation says doing all of this. Do all of this at the same time is basically the same as doing nothing. A plain wire is just the identity. Plain wire is just the identity. So this is a non-trivial equation. And I mean, you can do fun things when you got this cup-shaped state. You see, we've got a box there on the left. We just slide it to the other side. It rotates 90 degrees, which means having an operation on the left is the same as doing the transpose on the right. So that's what this shows. This calculation shows. If I've got a Bell state and I do an operation, Alice does an operation on the left, that is exactly the same effect as Bob does a transpose on the right. It's the same thing. So that's what this equation is saying. And here we got like post-selected teleportation. So all the shape of this cup and this cap together is really basically quantum teleportation. So here you see Alice and Bob who share a Bell state, like the cup-shaped thing. And then Alice does the post-selected effect, Bell effect, and then you can just slide that box without an input, so nothing comes out. Slide this box all the way to the other side, and so whatever, and that's a state because it doesn't have input. So whatever state Alice has there ends up at Bob's side. I mean, I'm going very quickly over this. In the book, this is many tens of pages to explain this all in detail. And then, of course, this is not full-blown teleportation, it's just post-selected. So basically, you see this unhappy phase on the left, that's actually the error, that actually allows you to take one of the 4 different effects in a Bell measurement, like via George-Jamelkowski, but then you can slide this box to the other side. And then, so you see, when you would slide that box to the other side, it's actually the edge on of the box on the left, which means if it takes boxes to be unitary, which they are, then they vanish. So this is full blown. And you got this wire in the middle. Now, this wire in the middle is an annoying thing because it is not part of picture, but in the full blown formalism, we can represent classical and quantum also in the same formalism. I'll give an example of that later. Okay, so now, this is all about these cups and these caps and these wires, and that happens to be not good enough to capture all of quantum. You need something more. Okay, and the thing you need more is something we call spiders. So, okay, so what is a spider? In order to understand what a spider is, we need to understand what a wire is, because spider turns out to be a generalization of wire. So what is a wire? A wire is a thing that connects 2 endpoints. You see here a wire and it has 2 endpoints. And now, so this is what a wire is. And now what can you do with a wire? What can you do with a wire? Well, if you glue 2 wires together, you take an endpoint of each of them, then you get again a wire. This is sort of the theory of being a wire. If you connect 2 wires together, you again get a wire. And there's nothing new which comes about. So it's quite a limited concept of wire. Now, what is a spider? You have to think of a spider as something like a wire, but not with 2 ends, but with multiple ends. Any number, or none, or 1, or whatever. So the number of ends can vary. That's the difference. And the behavior of such spiders is exactly the same as behaviors of wires, or generalizes it in the sense if you block 2 spiders together, then they fuse together, just like 2 wires fuse together. Of course, now the number of legs of the resulting spider may be different than the ones you start from, because you just have to count the numbers and keep them up. Here on the left, we got like, here is one with 5, there is one with 4, and we end up one with 7 wires. So that's spiders. Okay, so this is theory. Let me now just go a little bit off slides. So what's happening behind the scene here, say in Hilbert space? In the case that, suppose you interpret these spiders in Hilbert space. The way you would do that is, let's say these wires, they correspond to qubits. They're represented by 2-dimensional Hilbert space. And if you put two wires side by side, it's a tensor product of these qubits. So at the right-hand side here at the bottom, we got a tensor product of 3 qubits, and at the top, we got a tensor product of 4 qubits. Now, so okay, these are my types. Now assume that these green things are linear maps. So the one on the right, spider on the right, is a linear map from tensor product of 3 qubits to tensor product of 4 qubits. These equations, which I write down here, this fusion of the spider, together with its symmetries, is enough to prove a theorem. And the theorem is, in Hilbert space, each such family of spiders is in one-to-one correspondence with an orthonormal base. So this is a way to define orthonormal bases in a language where you only use this tensor product. So you can define orthonormal bases just using tensor product and for linear maps. You don't need anything else. You don't need an idea of sums. You don't need a notion of sum. You don't need to know coordinates and linear combinations and all of it. You don't need all of that. You can just do it with the tensor product. So this is a result very much in support of Schrödinger's thinking, I would say, because once you got orthonormal bases, you're getting close to measurements. And you can actually do this. You can actually use these spiders to define measurement. So measurement can be derived from the tensor product. And that very much feeds into sort of Schrödinger's thinking. Okay, so we now, whenever you see such a family of spiders, and we're going to distinguish them by colors, you have to think, I'm seeing an orthonormal basis here. I know it's weird. It's weird. It doesn't look at all like an orthonormal basis, but it is an orthonormal basis. Each is family of spiders. And okay. So what do we see here? We see 2 colors of spiders. So this means we have 2 families of spiders. So we have 2 orthonormal bases. And we have an equation here. You see there's an equality in the middle. And what is the equation saying? For these two families of spiders, if they share two legs, and this has to be two, not one, they share two legs, then these legs go away. So they disconnect. They disconnect. What does this mean for the corresponding orthonormal bases? It means that they're actually mutually unbiased. This is a definition of mutual unbiasedness of two bases. So again, it's not maybe what you would expect to be, but that's what it is, exactly on the nose. So you can define mutual unbiasedness in this way. And for example, examples of bases which satisfy this equation would be the Z bases and the X bases for qubits, because they're mutually unbiased. In the old language, people call this complementary. So we have got here these complementary spiders or mutually unbiased bases. What do you want? And they satisfy this. So let's recall our equations. Spiders of the same color fused together. Spiders of different colors. When they have two wires between them, these wires go away. And now let's see this on a very simple calculation. This is a totally trivial calculation. So as it turns out, if you take the green spiders to corresponding with the Z bases for a qubit, and the red spiders corresponding to the X bases, and you connect just look at the thing on top, like just look at the horizontal wire between a red and a green on top. Turns out that this is the C0 gate. You build a C0 gate by taking a red spider and a green spider. Now, you probably don't understand what I mean by a vertical wire, horizontal wire. Horizontal wire means it doesn't matter whether I actually take these wires in between them as an output or an input or whatever. It doesn't matter. It's always the same. You always get the same because of the symmetries of the spiders. So that's why we write it as an horizontal wire. So this is what we got here really is three C0 gates. We got three C0 gates here. We got three qubits. And on them, we have three C0 gates, with the green dot being the control and the red wire potentially unigate. Right? So now we want to simplify this circuit using our spider rules. Okay, let's look at it. Which rules can we apply? Well, I mean, we see three green spiders, which are connected, two red spiders, which are connected. So in the first step, we just fuse them together. Okay. So that's our first step. We fuse them together. And now we see there's two wires between the red and the green. Okay, they fall away. So they go away. So two wires between different spiders go away. And now we got a wire with a spider with two legs. But yeah, that's just a wire. We know that because spiders generalize wires. So we actually get this. So we were able to simplify this circuit to this circuit using the spiders. This is a very, very simple example, super simple example, super easy example, of course. But this generalizes, this method generalizes, and this method now constitutes the state of the art on how to simplify quantum circuits. So using this spider language and all that provides us with the best way to simplify quantum circuits. So this method is, for example, lives inside the ticket compiler. So Continuum, it's more than a compiler, but part of it is compilation, and it uses this method to simplify its circuits because it's part of the state of the art to simplify circuits. So that's pretty cool. Okay, so this is a very easy example. Now I'm going to go much closer to the end of the book. Okay, so this is a picture, and you see a lot more going on here. You just ignore like these wires which go between this red dot and this green dot. They're like a little bit like see, there are some cracks in it. Just ignore them. They mean nothing. So what do we see here? We also see that some of these wires are double. Some of these wires are drawn double, and some, like the one with these cracks, are drawn single. Well, when you see double wires, you have to think quantum. When you see single wires, you have to think classical. So in this picture, we have both quantum and classical things going on, because we see double wires and we see single wires. What else do we see? We see at the bottom a red double dot, We have like three double wires coming out. That is actually a GHZ state. That's a GHZ state. the GHZ state. And then you see these red double dots with one double wire coming in, one double wire coming out. They're actually phase gates. They're phase gates for the X observable. So no, not the usual phase gates for the Z observable, the ones associated with the X observable. And and when the angle they carry is basically the rotation they do. So in fact, the double red dots with one in and one out, they're actually just identity. They're zero phase rotation, but just for clarity, we put them here. So what you see here, and then the green dot, which goes from 2 to 1, is actually a measurement. It's a measurement in the Z basis. It's a measurement in the Z basis. Because it's green, it's a measurement in the Z basis. Okay, so what we see here are 4 GHZ states on which each case 3 measurements are done, but because of the rotations, these are different measurements each time in each of these 4 scenarios. So these are actually the 4 scenarios of the GHZ Mermin non-locality proof. These are the 4 scenarios you consider. So you do all these 4 scenarios, and then what you do, if you know maybe you don't know the argument, but the argument is then you take these 4 scenarios and you do a parity check. You look at all your outcome of these measurements and you measure parity, the overall parity. So this red dot with single wires is actually a parity check, or you can, it's an XOR, you know, parity and XOR is the same thing. So it's a big XOR if you want. And okay, so then you can compute this thing, and I'm just going to get, I'm going to informally say what happens if you do the computation. All at the bottom, all the red dots, they fuse together. All the red dots, they fuse together. And then on the left-hand side, we got no angles. On the second one, it's under 80. The third one is under 80, and the fourth one is under 80. Because when spiders with decorations, so these spiders, they carry decorations. So we generalize our spiders to carry decorations. When the spider with decorations, when they fuse, these decorations add up. So this is a new concept which I didn't introduce yet, these angles on these spiders. But it's something which exists for just abstract nonsense reason, really generalized nonsense reason. But every spider naturally comes with these phases, and these phases always form a group. They form a group which we call the phase group. So, okay, so in this calculation, we have now all these red things having fused together. And then it turns out that from the equations of spider interaction, you can actually commute the red dot and the green dot. And then this red dot is on top, and they all fuse together. That's really the calculation. You find this in our book. In both books, you find this calculation. It's not difficult, but I haven't given enough background to do it properly. Because this is actually on page 120 or 130 we're talking now. And then basically you got all these angles are going to add up, and we got 180 plus 180 plus 180 gives 180. And it turns out the red dot decorated with 180 is the 1 bit, is the bit, the classical bit 1, is 1. Okay, now here we see a different diagram, and what this actually is the articulation, the expression of locality. So that the existence, the fact that there is no local hidden variable theory possible. So what you see here, these boxes at the bottom are actually, so you see on each particle here, there are 2 possible measurements, either with 0 angle or with 90 degrees angle. So these 2 boxes, the one without star correspond to the hidden variable for the measurement with 0 angles, and the one with stars for the hidden variable for the measurement with 90-degree angles. And we do this for each of the 3 systems of the GHZ state. So that's what these variables on the bottom do. And then we copy these variables out, these classical values out, to the different measurement scenarios which live in the middle. I mean, you probably can't map, but at some point in the middle, you'll see there are 12 wires, which correspond to the 12 wires coming out here. But now as an hidden variable, as a local hidden variable. And then we do the parity thing again. So this is the expression that this is the statement or the assertion that there exists a local hidden variable model for whatever happens in the previous scenarios. Now, if you look at the green dot and the red, there are always exactly 2 wires between them. There are exactly 2 wires between them. so they fall away. So what we end up at the top is just a red dot without an angle, and that turns out to be the classical bit 0. So quantum gives 1, hidden variable gives 0, contradiction, there is no local hidden variable of quantum, and that's exactly what the Nobel Prize this year was given for. So this is the diagrammatic proof. This is the most complicated thing you find in the whole book, but it's actually not complicated if you've gone through the whole theory. But it should show. So, for example, here this is Dan Gicca who posts a review that was on Facebook, I think, from Alexander Gicca, his son, age 10, on the new book, and he understood everything. So it's 10-year-old, he understood everything. So even states very well structured, easier to understand than science YouTube videos. So okay, so that's good. Now, of course, this is just one person. So what we are doing now at the moment, and this is in collaboration with Oxford University and IBM, is we're setting up an experiment in which we teach teenagers quantum through our new book. So they don't need any math background. And at the same time, we're going to consider a bunch of Oxford students who take a regular quantum computing course, and we're going to subject them to the same exams. And then we're going to see who performs the best. So the timeline now is that we start our lectures, because we've got these video lectures, that will be the lecture for students, then they will get some tutorials and things like that. They would get the regular course. So we already have been collecting volunteers, so that's all done now. And so the next thing is basically to educate them in quantum. We use exactly the same time frame as courses at Oxford University take, and then we're going to give them an exam in the same format as Oxford University, of course, formulated in terms of pictures, because otherwise they wouldn't understand the question. They don't know Hilbert space. And then the Oxford student get the same questions formulated in Hilbert space. So that's going on now. And then we hope to show that effectively teenagers can even outperform Oxford University students on certain tasks with these diagrams. Now, what's the origin of all that stuff I've been talking about? The origin of all that stuff I've been talking about is something called ZX calculus. So the name became, I mean, because he was sort of an axiomatization of Z and X observables or Z or X basis, but it's actually much more general than that. But the name ZX calculus has stuck, and he was Ross Duncan, who's now the head of software at Quantinuum, and myself, who came up with that in 2007, so quite a while back. And for some reason, it didn't pick up very well initially. People, it was very weird. It was an interesting sociological observation. People for a long time the mainstream community for a long time didn't believe that something that looked so simple could actually be useful for anything. And they never even bothered to study, they never bothered to learn, they just had a judgment as a mainstream community. Okay, that stuff. Some people kept working on it. We kept further developing the theory and stuff like that. And then a few years ago, there was a complete switch. And because quantum industry came about. So quantum computing is becoming closer to something practical, and as practical needs, like making circuits as simple as possible, error correction and stuff like that. And suddenly people start to realize, initially in quantum industry, that this stuff is super useful actually. That this stuff is not just useful, but necessary for many practical applications. So the domain where I think it's now most widespread use is photonic quantum computing. So companies like PsiQuantum, who are trying to build a photonic quantum computer, are using this basically as their main language. So they're now using ZX calculus as their main language to describe things, not Hilbert space anymore. The reason, of course, they do measurement-based quantum computing. Measurement-based quantum computing is horrible in Hilbert space, just horrible. While actually, historically, ZX calculus came out of problems in measurement-based calculus. So measurement-based quantum computation. So they go very naturally hand in hand. And so here you see that ZX calculus is immensely useful graphical language for blah, blah, blah. So they use it as their main language. PsiQuantum is the biggest photonic quantum computing company in the world. And then the cherry on the cake recently, this is very recently, we're talking 2023, is if a paper came out on error correction with Peter Shores, co-author, and he's advocating the use of ZX calculus for error correction. It's even stated there that everybody doing error correction should be using CX calculus probably. So it suddenly there was a complete change, and then it's now fully embraced by quantum computing world and all that. And okay, this is so there are two dimensions here to the story. One dimension to the story is the educational value of this formalism, because it actually can make quantum much more inclusive than one would have expected with the Hilbert space formalism, because many more people can now learn quantum through these pictures. And I think this is very important, especially with what has been happening recently in AI. In AI, a bunch of people just went wild, like they were like wild cowboys, and they did whatever, and nobody understood what they were doing. And now we're in this situation that actually we're stuck with something that seems quite dangerous. With one of the fathers of the field, Hinton, denouncing his own work basically, and that he's sad that he actually did it, and that this maybe shouldn't have happened, and it's a very dangerous thing. And by making quantum more inclusive, we actually can avoid such situations as which have been happening for AI. So that's the educational side, and then the other side is what I'm just saying here. That is really very important for practical quantum computing. These diagrams, people now want to use this because it solves problems which are otherwise hard to solve. Like I already said, circuit simplification, so it's widely used for error correction too, in many different ways. There's many other, like I said, photonic compilation, many different applications now are using these diagrams. I mean, this is now an outdated slide, but this is the places I was aware of at some point where they're using these diagrams for some reason or another. It's not just quantum computing companies, it's lots of different kinds of companies that you see here. They're using them at NIST. For NIST were actually one of the early ones where they were using them. So yes, you see NASA, so they are now really widespread used. And I'm probably missing so many out here because I stopped catching up. And there's probably some who just don't say it. Right, so why is this language so powerful? Why is this stuff so powerful? Well, this is a theorem from, essentially the main theorem came out in 2018, where people in a number of stages have shown that any equation you can derive using Hilbert space, linear maps and all that, you can derive with these diagrams too. So there's nothing more equations that you can derive in Hilbert space than whatever you can do with these diagrams. So they are, that's the technical term which logicians use, they're a complete axiomatization of Hilbert space. They're complete. That's where this works. So of course, they're of course also universal. Also, otherwise they were pretty useful. So what I mean by universal is you can write down any matrix in terms of the spiders. Any matrix can be written down in terms of the spiders. But what I'm saying now is much more. It's any equation between matrices and whatever you do with them, that can also be derived using these rules of spiders, like fusion, legs falling away and that stuff. You can derive everything you can do in Hilbert space, any equation. So it's a very powerful thing. That's okay. So that's the end of this part of the story. I've got another part which is much shorter, I guess. I wanted to be clear on this one. And this other part starts with this person. This is Jim Lambeck. So Jim Lambeck is a category theoretician, but he's also father of something which is called computational linguistics. He came up with a system around the 1950s, that allowed you to check whether a sentence is grammatically correct. I'll explain a little bit how this works. So he came up with this system which explains how a sentence is grammatically correct. I'll get to that back. Now, so Jim, unfortunately, he died a few years ago, and but he was a professor at McGill, Montreal, Canada. And so 2005, which is the time I wrote kindergarten quantum mechanics, so the first time I wrote this paper with these diagrams, I was in Montreal and I was giving a talk about, say quantum teleportation in diagrams. Like I said, I showed these people this picture of quantum teleportation and I explained it. And then Jim was in the audience and Jim said, Bob, this is grammar. Huh? No, this is quantum teleportation. This is quantum physics. I said, no, Bob, this is grammar. This is exactly the structure of grammar. And he was right. As it turns out, if you look through category theory glasses, the structure of these teleportation diagrams and the structure he came up with He came up with different ones, and this was one he came up with in 1999, is exactly the same structure. And I'll show how the sort of things we saw before, the cups and the caps and all that, allow you to actually verify grammatical correctness. So I'll show this. So I didn't care. So I mean, this was 2005. I was just starting to come up with this new quantum formalism. I just thought of this as a freak artifact, and I didn't take more notice than that. I didn't take much more notice. However, a couple of years later in Oxford, I had some colleagues there, and one colleague was Marnusha Derzadeh, and she knew about this Lambeck algebra, this Lambeck grammar calculus. She knew that stuff because she had done it for Lambeck. She had developed the theory specifically for Persian. So she knew that stuff. I never even bothered to look into it. Okay, I can say that. And then there was also, I'm going to explain a little bit how this works. I'll be very brief here. So basically the idea of these grammatical algebras work is you got something called basic types, basic grammatical types. And these are things which make sense on their own, like a noun. A noun makes sense on its own. It can be an answer to a question or something like that. And the noun type, we give the symbol n, and it's a symbol for the noun type. And a sentence, of course, also makes sense in its own right. So the sentence also is a basic type called S, basic type. And then there are things which don't make sense on their own that easily. And an example there is, for example, a transitive verb. A transitive verb because it wants a subject and an object. In English, the subject on the left, the object on the right. In other languages, they may be different, but it always wants a subject and an object. So I'll now develop types for English. And the way you express this, wanting a subject or a noun on the left and a noun on the right, is by, you see that symbol, like I've got an S and then I've got an N on the left with a -1 and an N on the right on -1. These -1 are sort of at the different sides of the ends. And basically what this means is I want, so it's like an antiparticle. Think of it as an antiparticle. So an antiparticle wants a particle to get annihilated. And so here, this is saying this transitive verb needs a noun on the left and a noun on the right so that they can cancel out. Exactly like I show in this calculation here. You see, the three things in the middle are a transitive verb. I stick a noun on the left, noun on the right, they cancel out, and I get a sentence type. And this is actually the proof of the grammatical correctness of in English of transitive of noun, transitive verb, noun. Now, the important thing is you can actually represent this calculation using a diagram. And the sort of annihilation of this n and this anti-n, so to say, we can represent this by a cup-shaped wire. Same here, same on the right-hand side, we can cancel them out via cup-shaped wire, and the sentence type is retained, it continues. So here you see a little diagram, and this diagram actually witnesses the grammatical correctness, the proof of the grammatical correctness of the sentence noun, transitive verb, noun. And you can do this for any grammatically correct sentence. For every grammatically correct sentence, you get such a diagram, which witnesses the proof of correctness. So what we have now is grammaticality is witnessed by such a diagram structure, right? And this is nice. Now, we had somebody else in Oxford, and that's Steve Clark. Steve Clark is now our head of AI at Quantinuum. And he knew something else. He knew what I call meaning mathematics. So meaning mathematics is what all the chat GPTs and all now use today. At the time, this was purely an academic discipline, and it's basically representing meanings of words by vectors. So that's what Steve was doing. He was studying the ways you can represent meanings of words or vectors. Yeah, so this was basically about words. They actually had a term, the bag of words. They didn't care about grammar. They just looked at individual words and how meanings can be related. That's what they were doing. So on the one hand, we've got a theory of grammar, and where you compose nouns and sentences, grammatical types. And on the other hand, you have a theory of meaning about single words. Now, a natural question is, how can you combine them? Can you combine them in some way? Because we as humans, we basically use grammar to provide meanings of things like sentences. So if you understand the meanings of words and we form a sentence with them and it's grammatically correct, then that sentence is meaningful and we will understand that sentence. We don't have to look it up in the dictionary or something like that. And so can we come up with a mathematical theory where if you know the meanings of the words and you have the grammatical structure, you can actually spit out the meaning of a sentence. And I mean, so Steve asked this question, he formulated this problem, like we don't know how to combine meanings of words with these grammars. And then I remembered, of course, what Jim had said, that the structure of the structure on the one hand of quantum mechanics, the teleportation stuff, which really is vector spaces and their compositions. So we're talking about vectors and compositions and things like that. Looks exactly the same as the structure of grammar. So it was easy to imagine an algorithm which combined the two using basically our diagrammatic quantum formalism. So the idea is like you use the diagrams, they represent the grammar, and what flows in the wires are your vectors, your meaning vectors. So that was the idea we had, and I'll give an example soon. So this came out in this paper, Mathematical Foundations for a Compositional Distributional Model of Meaning, where we start to formulate and this way of like composing meaning, and this is how it works. So what you see here is actually an algorithm. This is an algorithm that computes the meaning of the sentence. The sentence Alice hates Bob. This is our algorithm. It computes the meaning of sentence. What are the ingredients? What you see on top are the meanings of the words. What you see on top are the meanings of the words. What you see on the bottom are the grammatical structure. And this is now interpreted as a linear map that is applied to these vectors, to these word meaning vectors. So now we're reading from top to bottom, because in English you write your text from top to bottom. But so you see this cup-shaped wire. This is actually now like a bell effect, which it's almost like Bob is teleported into H, Alice is teleported into H. H is like an entangling gate. Think of H, it entangles Alice and Bob in a hate relationship, and that's what comes out. That's the meaning of a sentence. The sentence said at the end of the sentence, or at the end of whatever happened, Alice and Bob are entangled in a hatred relationship. It's a very non-symmetric. So of course, a very non-symmetric gate or a non-symmetric relationship. So that's it. And then you can, for example, start to compute inner products. This is like a sideways written inner product, which computes whether Alice hates Bob is closely related to Alice does not like Bob, because using the product to actually compare similarity of meanings. Okay, we use spiders too in this theory. I'm not going to go into that. Okay, so when we came out with this thing in 2010, so people start, I mean, I was telling my co-authors, don't mention the word quantum, because people are going to think that we're crackpots combining quantum and language. And there was all these headlines, quantum linguistics, the quantum linguist, quantum mechanical words, and so on. Okay, but there was some truth about what they were writing, because what we were doing is we used something that looked very much like quantum mechanical formalism to do linguistics. Now, this is actually not necessarily a good thing. This is not a good thing. Why? Because, as Feynman said, like if you're going to take a system like a chemical system or something that is described by quantum mechanics, in our case, this is this meaning theory, then it's going to be pretty hard to do on a classical machine. And we, of course, we did lots of experiments. We got incredibly good results. But with our new theory, but we had a hard time scaling. It didn't scale very well. The reason was these tensors and these meanings, they very quickly became very large, and a bit too large for classical machines to do it naively. I mean, we had ways to do it on classical machines, still doing it now today, by the way, but it wasn't the obvious thing. Now, okay, we're much further, and now there are quantum computers around, and in 2016, for example, Rigetti started as a company, and then this is Will Zhang, who did my PhD at the time with me, and then moved to Rigetti. And we basically asked the question, now suppose we're going to stick this theory in a quantum computer, this new theory of meaning. Do we get any quantum advantage on top of that? He wants to live in a quantum computer like chemistry, but maybe we get also quantum advantage for some algorithms. And it was very easy to see that for most typical natural language processing tasks, such as classification, sentiment analysis, you effectively get like quantum advantage. You get quantum advantage. Now, this was 2016. Quantum computers weren't that big yet. Okay, now 2020. In 2020, we for the first time effectively did quantum natural language processing. So natural language processing on actual quantum hardware. We did some question answering tasks and things like that. And we got very good result. It worked very nicely. This was still on very small like data sets, small machines and all that. Then, of course, then we start to try to do it bigger, which we did in this paper, QNLP in practice, which is now published in one of the main AI journals since a few weeks. And next thing we did is we took all that software which we had developed to do this quantum natural language processing, and we made it really nice, and we threw it at a public open source. So everybody can now, you can go home and you can do quantum natural language processing yourself. You use our software, and it's open source, and you use one of the freely usable IBM quantum computers, and you can just do that, or a simulator if you want. So you can do it yourself. So the software is called Lambeck. Not a surprise, Lambeck, you remember Jim Lambeck who made this comment, but now with a Q at the end. So this is our paper, and if you want to know how to do the quantum natural language processing with our software, it's all explained in this paper. And it's not, we got like this big international community now with a Discord channel, like hundreds and hundreds and hundreds of people doing this stuff. Now, sometimes for fun, sometimes actually to try to do something useful. Then once the software was out, of course, other teams, other companies actually started to use it. So this is a paper by IBM, who actually tried to even further scale up the size of the type of experiments you can do. So this is an IBM team who did this in 2022, it seems. And this is another IBM team, and they also used our stuff, and they actually did it to start doing quantum natural language generation, which we provide a classifier, and then you can actually also do generation. So that's another IBM team who did like has been using our stuff to do generation. They actually wrote a really nice blog post. So an introduction to quantum natural language processing, and it's probably the best place to first read about all the things I've been talking about in a not too complex way, like not at the level of papers, but a little bit more informal, like in a very well-written blog post. So that's a good place to read this one. What did we do? Meanwhile, well, we did a lot of stuff, but one thing I definitely want to mention is the following. We basically took the linguistic grammar and instead put in a musical grammar. This didn't exist. And then we started to generate music on the quantum computer. We generate music on a quantum computer using like musical grammars. And this is a software which is also available, Quanthoven. You can, it's open source, you can get it. And so you can do all this stuff yourself. The funny thing is we generated some songs. One of them was Bob's Cigar Bus. It actually ended up #1 in some classical charts. And I think looking at the time, this is probably a good time to stop my talk. So we have a chart success. Okay, so let me go to the end of the talk. You can follow the things and other talks and publications on Twitter, where where I basically post everything that I think is relevant. Okay, thank you.
Thank you, Bob, for a very stimulating talk. It's now open to questions. So people who have queries, they can ask. Santa, you are muted.
Yeah, I would like to ask a question. First of all, Bob, it's a wonderful talk. So, when we're looking at natural language processing, do you really see quantum has some natural advantage? Like, for example, when we produce the language, when we come up with grammar, is there any quantum process going on in our brain, for example? Is it reflective of that?
No. I don't think there's anything quantum about language per se. What is happening here is that there is a certain type of structure, call it a logical structure, which is represented by this diagram and which is pretty much all around us. But we never look through those sort of glasses. And when you look at the world through those sort of glasses, you see that many different things, which you usually don't see any connections between, actually start obeying the same kind of logic, so to say. I definitely wouldn't call this quantum logic or anything like that. It's a certain logic of composition in which, so in the traditional world, people always think that most things are separated. Like I got two things, I got a pen and this. But actually, in reality, if you look at the world, things are not separated. If you look at words, they're talking to each other, the words, of course, through the grammar. If you look at people, what makes a human? Human is characterized by its relationship with other people. Not what it's made up, the person is made up from. That's and you see a lot of things in the world are about how things are related to each other. And what this logic is basically expressing is the most simple logic of like non-trivial relatedness. And this makes sense for language totally. This makes sense for quantum. Quantum is what forced us into looking at these things. With Schrödinger discovering entanglement, suddenly the world didn't exist anymore in physics about separable things. And so it's a logic of non-separability on the one hand. So now, part of your question was about advantage, of course. So this language model we have now, because of its similarity with quantum, is quite hard to simulate. It's a hard tensor network, hard to simulate on a classical machine. So you already get an advantage on a quantum computer because on a quantum computer, all this exponential blow-up vanished. It's very easy to simulate. But now we also think, and this is not in papers or anything, that we could even get exponential algorithmic advantage by doing natural language processing on a quantum computer. To be honest, so what do we do now? Let me talk from the perspective of AI. What we do as compared to usual AI is that we bring interpretable structure into the picture. Literally, it's like you really see the structure of the language in the diagrams. I mean, these were very simple diagrams I had, but you see that, and I don't think that anybody could do anything like natural language processing on a quantum computer without the help of that structure. Like if you do it brute force, like the big language models do, would be impossible. Because it would be impossible to train a quantum computer. But it's actually that structure. It's an expansive structure. It's tensor structure and all that lets us even do it for now. And it also makes it interpretable. So in the current discussion about AI being dangerous, we're in a very good spot. We're in a very good spot. So there's a number of advantages. And so in our experiments which we're doing, so we're hoping to demonstrate this year algorithmic advantage. Like not just advantage, actually supremacy. We're hoping to show that. Then you got the interpretability advantage, and then you also got the reduction of resources advantage, because you got an interpretable structure, which means something. You need less data and less variables.
Yes. Yeah. Thank you for a wonderful talk. Thank you. Yeah.
Anyone else? And any question?
I wanted to ask a question regarding your pictorial method. So is it that only processes which has time ordering can be represented through this pictorial order, or like any general process can be represented?
So there are papers already using this sort of language or similar to do like indefinite causal structures.
Yeah.
So Alex Kissinger has a paper, has quite a number of papers, Giulio Cherabella has papers where you use the same formalism to deal with indefinite causal structure. So no, it's the way you have to think about it is like, in that case, you don't stop at process. You also stop at higher order processes which change processes. What people call combs, these combs.
Okay.
This actually is true for language too, by the way. If you got an adverb, let's think of a verb will be a gate. We typically think of a verb as a gate, and an adverb will be something acting on a gate, modifying that gate. That's what an adverb really does. So you need to go to higher order processes to capture all these things, but then there is no problem.
But will it give an advantage in the pictorial method?
I mean, in a lot of the sort of indefinite causal structure stuff, people are just using these graphical language because it's just easier. I mean, superoperators are pretty horrible things in Hilbert space.
Yeah, but what sort of constants will you have here, like on the pictorial constants? how will you transform one? Let's say I have the algebraic expression. How can I convert it to a pictorial constraint or something like that?
How can you what?
How can I convert that into pictorial sense? Like let's say I have a constraint, algebraic constraint, and I want to visualize it pictorially. I mean, what kind of like how can I transform that language into this pictorial thing?
Okay, so at the moment, what I've been talking about is a context where you, for example, don't have differentiation or integration or exponentiation or Hamiltonians. Now, if you go to some recent papers by us, then you'll see that we have now developed these diagrams also to do like analytical stuff, integration, differentiation. There is a bunch of papers which are about like how to formulate field theory, quantum field theory in this language. So you have to look for papers by Stefano Goggioso, who does this. So this sort of developments to like general physics are still very much in progress. Mm-hmm. But we since recently we've got essential ingredients there. So we're now, for example, studying with the chemists in our company to see whether we can get an advantage for quantum chemistry. So they give an Hamiltonian and we start to study Hamiltonian diagrammatically. That's ongoing research.
Okay, thank you.
I'm not really hearing.
Anyone else? Okay, if not, Bob, thank you again for a very wonderful talk. It was nice having you here.
Okay, thank you. Bye. It's lunchtime here.
Yeah. Thank you, Bob.
Bon appetit.
Bye. Yeah.
Thank you, Tavi. It's very wonderful talk. You know, this guy is so creative, Bob.
Yes,
My God.
Thank you.
Wonderful.
Thank you. Cheers. Bye. Cheers.
Bye. Yeah.
Okay, then. Bye-bye.
Bye.
So, Swami, can we log out for tomorrow?
Yeah. So I think we'll end the session now as we have no more talks. And tomorrow the session starts at 9.
Achha,
9, right.
Yeah.
Okay.
With,
please send a gentle reminder to all, huh?
Yeah. We'll send the mail to everyone.
Yeah.
And I think tomorrow the first talk is from Professor Barry Sanders.
Yes. Yeah.
Okay.
Thank you.
Yeah.
Right. Okay. Bye.